Hello geometry students, this is Mr. Fugay, and this video is going to be our first lesson of our second unit talking about the basic triangle properties. So you should have a note sheet or something similar looking that what you see on the screen, and we're going to go through a few important properties, baseline properties that are really going to help us build our understanding of triangles, which is something we're going to study for the majority of the rest of this course. So let's start with the most basic one that maybe you might remember from before, but if not, here's your refresher. And it's formally called the triangle sum theorem, but you might just know it as, oh, all the angles of a triangle must add up to 180. And that's exactly what the triangle sum theorem is. So the three angles of a triangle sums to 180. And if you look at that diagram listed below there, that triangle ABC, what that means is specifically I could set up an equation to say the measure of angle A plus the measure of angle B plus the measure of angle C equals 180. And we're going to use that for the two examples below. But don't just take my word for it. Let's take a moment. If you need to pause this video, you should see two hyperlinks down below, a visual proof as well as a geometric proof. So take a moment if you would like to look at either of these videos or both of these videos for a more deeper dive into why this is true. Remember, we've talked about the word theorem, meaning something that should be proven before we start using it. So take a moment to prove it to yourself, and then when you're ready, we're going to hop down to these examples. So here we are. Triangle sum theorem. Now you probably are looking at this and know, oh, I'll just go in my calculator and I know that all three are 180, so I'm going to go 180 minus 80 minus 35. And while that would absolutely give you the correct answer, let me show you formally what we want to show here. We want to write the first angle plus the second angle plus the third angle equals 180, and this will help with our second example. So I'm sort of previewing coming attractions here. So 35 plus 80 plus x equals 180. We know that those are going to add to 115. And you can see the numeric process that you probably just went ahead and did in your calculator is the exact same thing as what I just showed here on screen. So that third angle must measure 65 degrees. But if we look at the second example, you will see now that we don't have that intuition that we can use on the first one. So we are going to need to look at a more formalized algebraic process. So my first angle plus my second angle plus my third angle will then equal 180 degrees. We'll then go through the algebra process, combining like terms on the left-hand side, still equal to 180. We're going to subtract that 70 to the other side, and finally divide by the 10. X is now 11. Now we can plug this 11 in for each of these x values, and when we do that, we get 61 degrees, we get 107 degrees, and we get 12 degrees. So we can write those down, and one good way to check that we've done this correctly is make sure that the triangle sum theorem does work out, meaning all three of those angles are going to add up to 180 degrees. So that's part one. This is a three-part. We're going to chunk this into three sections. So let's look at the second part of this lesson, and that is triangle types. Now you again have probably seen these words already. We've already talked about acute, right, and obtuse. Scalene, isosceles, and equilateral are probably words you've heard in the past. So let's jot down their definitions real quick, and then we'll look at the diagram below. So we'll start across the top. Scalene triangle is a name of a triangle with no equal sides or angles, meaning all three sides are different lengths and all three angles are different measures. An isosceles triangle has two equal sides, let's space that out, equal sides slash angles. This means it will have two equal sides. It will also have two equal angles. We'll talk specifically in another lesson about where they are in relation to each other. I'll give you a little spoiler when we draw the picture below in a second here. And then equilateral is when all three sides are equal. I should probably say all three sides and angles are equal. Let me write that down instead. So another term, sometimes an equilateral triangle will also be called an equiangular triangle. Okay, let's talk about acute, obtuse, and right. So an acute triangle is a triangle where all three angles, well, are acute, but we'll go ahead and specifically say less than 90 degrees. I don't want to use the word in the definition. A right triangle has one 90-degree angle, and then the other two are going to be acute angles. And finally, the last one here, obtuse, is going to have one angle that is greater than 90, which is, again, by the definition, an obtuse angle. And then the other two must be acute angles. Now, a question I want you to ponder and think about that we'll talk about in class is, why are triangles only allowed to have one angle as a right/obtuse? So you'll notice the definitions there. Think about the reason why that is, and it ties into part 1 of this lesson. Now, let's look at a sketch here of what these triangles would look like, because a triangle, for example, could be scalene and acute, meaning it can have a classification for its sides and a classification for its angle measures. Made that a little sloppy there, okay? So an acute scalene triangle, quite literally, is just going to have 3 different sides, 3 different angles, but all of those angles are less than 90. That's it. A scalene right will have maybe a short side, a long side, and then this side, but notice that the big change here is that we have specifically a right angle in the drawing. But all 3 sides are still different. And finally, we have an obtuse scalene, which again, 3 different lengths. All 3 of those lengths are different. And what you'll notice is one of the angles down here, that's our obtuse angle that will specifically classify it as being obtuse. Now, in the isosceles column, an isosceles acute triangle, again, all the angles must be less than 90, so maybe it looks like this. And these 2 sides are going to be equal. Now, we'll talk about this in the next lesson, but that also tells me that the 2 equal angles are actually down here. They're called base angles, but we'll talk about that in another lesson. In an isosceles right triangle, we're going to have 2 sides that are the same. Let me keep the color the same here. So it's going to look just like this. We're going to have our right angle. We're going to have our 2 equal sides. Now, if you want to talk about the 2 equal angles, they would be the other 2 angles that are not 90 degrees. So take a little question there on the side, a little side quest. What would those 2 angles have to measure then? I'm not going to answer it, but let you think about it. And then finally, the obtuse isosceles triangle. Let's see, make this a little bit long enough so that we can see that the angle across the top, at least I'm trying my best here. Sometimes it's hard to draw these things freehand without, so it would probably be like a skinny triangle that looks like this. And so my obtuse angle is going to be right here. Down here would be the 2 equal angles, and then these would be my 2 equal sides. So a lot of information there to be marked. And then finally, our last one is our equilateral triangle, where all 3 sides are equal, and as well as all 3 angles. Another little side quest I want you to think about is, it is impossible for a triangle to be equilateral and right. It is also impossible for an equilateral triangle to be obtuse. So there are no possible triangles to draw there. So think about why that is. Why would that be? Okay. All right, we've moved on. That is part 2. Let's talk about the final section here, and that is talking about exterior angle theorem. But before that, we should probably talk about what an exterior angle is first. So let's jot that down. So that's an angle formed outside of a shape. More specifically, a polygon maybe, but we're going to talk about triangles, but we'll say in shape. The other key here is it is a linear pair with an interior angle. So what do I mean by that? Well, let's draw a picture here below of a triangle. And what I'm going to do is I'm going to extend all the sides here. All the sides. Like so. So let's just focus maybe on this bottom intersection here, bottom left. So in red, these angles would be your interior angles. We know that they add up to 180, by the way. So an exterior angle, I'll use blue for this, is going to be this angle right here because it is a linear pair with an interior angle. Also, technically, this would be considered an exterior angle as well. So these are some examples. Now, on the other two sides, if this will let me zoom out, there we go. This is also exterior. This is also exterior. Notice all of these are linear pairs, okay? Now, what is sometimes creates confusion is that these ones that I'm creating in green are not exterior angles. They are actually vertical angles with your interior angles, so they do not have any special classification. Okay, so let's talk about that last example then. So what we now can create is something called the exterior angle theorem. Now, rather than me writing down what it is, let me explain how it works. I'm going to write down two statements that we've already learned from this lesson and prior. The first one is that the measure of all of those interior angles are equal to 180. This is the triangle sum theorem that we just got done talking about. In addition, there's another pair of angles that add up to 180 here, and that is going to be angle C and angle D. The reason why they equal to 180, well, by the definition, they're exterior angles, but also more specifically, they are linear pairs. Now, technically, since these three angles equal 180, and these three angles also equal 180, I could make a brand new equation that says, well, the angle A, angle B, and angle C have to then equal angle C, let's put a little M there, and angle D. That's really just what we would call in math a substitution. So on the right-hand side, I'm just jotting down like my thoughts of why I'm writing that. Now, because there is an angle C here and an angle C here, we could essentially subtract them away from each other, creating our final form here, which is that the measure of angle A plus the measure of angle B equals the measure of angle D. Now let's see what that looks like over there. So we have A and B. If we would add their angles together, okay, then that would equal what angle D is going to measure. That's the theorem. Now, more generally, what does this mean? It means that an exterior angle is equal to the sum of the non-adjacent, so the ones that it's not next to, the one that it is not next to, I should say, interior angles. And the reason why is what I just showed you above. It's essentially combining the triangle sum theorem with the definition of a linear pair to create a new relationship that we can use in future problems. So to wrap up this lesson, let's take a look at two examples of this. So in this example 3, we have ourselves our exterior angle sitting here on the outside, and then inside we have this x value and this 90 degree. These are your non-adjacent interior angles to the 150, because the adjacent one would be this one, so we don't want to use that. So the triangle exterior angle theorem says that I can take my exterior angle, set it equal to the sum of those two non-adjacent interiors. So then when you subtract 90, we're being told now, oh, well, that missing angle then would have to be 60 degrees. Now, if we wanted to do this the long way, technically you could still find this answer, and here's the reason why. I could effectively say, oh, well, 150 and this angle are a linear pair. That means that this is going to be equal to 30. And then because this is 30, because this is 90, the triangle sum theorem tells me that x has to be 60. And while this works for a numeric example like example 3, there might be a situation where this becomes actually difficult. And that brings us to our last and final example in this video. If we take our exterior angle, 21x plus 4, and then our non-adjacent interiors, we can set up an equation. 21x plus 4 equals 84 plus 10x minus 3. As we go ahead and speed up the solve for this, I'm almost out of my time. I don't want to take these over 15 minutes. We're going to get 77 equals 11x, and finally x is equal to 7. We can now take that and plug it in for those angles. And when I plug the 7 in, GST becomes 151, and UST becomes 29. That will conclude this video. So I hope this was helpful. Have a great rest of your day.